Hello, I'm Stephen Wilson, and I lead the development engineering team. We are part of the broader Boston Children's Simulator Program, SimPEDS, a program responsible for providing essential and life-like rehearsals at the points of greatest impact to optimize outcomes for clinicians, staff, patients, and caregivers. This development engineering team is responsible for creating and maintaining novel healthcare simulation trainers and devices. And we also maintain an in-house 3D printing anatomic modeling service. The service makes use of state-of-the-art hardware, software, 3D printers, which are all centrally located in our studios here on the Longwood Medical Campus in beautiful Boston, Massachusetts. We provide digital and 3D printed anatomic models to various surgical departments, such as orthopedics, plastics, cardiac, and neurosurgery. The 3D anatomic modeling service is responsible for the purposeful transformation of patient imaging, such as CT, MR, and ultrasound, into 3D anatomic models, and the rapid delivery of these patient-specific medical devices intended for use in patient diagnosis and treatment. Our team consists of formally trained engineers from various backgrounds with a combined experience of over 30 years in 3D anatomic modeling. Over the next few minutes, you will meet some of these engineers as they describe the Boston Children's Hospital Simulator Program's 3D anatomic modeling service.
Hi, I'm Mona Safarzadeh, and I'm a simulation development engineer at SimPEDS. We deliver hospital-wide 3D print services by producing patient-specific digital and 3D printed models of patient anatomy for preoperative planning.
The 3D models are intended for use in the diagnosis, treatment of the patient, as well as patient family education. Any anatomy that can be visibly distinguished on imaging studies can be 3D modeled and printed at SimPEDS.
The virtual or 3D printed physical anatomic models are delivered for 4 purposes: pre-surgical planning, virtual surgical planning, learning research education, and patient family education. Anatomic models for pre-surgical planning are used for adjunct visualization tool for delivery of customized models for surgeons, aid in diagnosis, develop and trial surgical approach, hardware guidance, hardware sizing and trial, and communication tool within surgical team and between members of multidisciplinary teams.
Virtual surgical planning begins with creation of anatomic models and includes any digital manipulation of the model and subsequent printing for diagnosis and treatment planning. VSP models are used for implant guidance, implant design, tool design, and surgical approach design. Anatomic learning research education model development begins with the creation of an anonymized anatomic model to enhance anatomy learning or better inform complex research cases. Artistic liberty is taken by our engineers to develop these education models to make the model look more realistic.
Hello, my name is Mariah Giarratano, and I've been with the Simulation Development Engineering team since 2016. Over the past few years, we've been fine-tuning our service by developing the expertise required to cater to the demanding schedules of clinicians. To create a model, the clinician simply needs to identify the patient, imaging desired, and the anatomy of interest. Our engineers have access to the imaging themselves to begin creating a 3D model. Engineers work to segment or isolate the anatomy of interest by highlighting them slice by slice to generate a digital model. This digital segmented model is reviewed and approved by a radiologist and then exported to a CAD software specifically for preparing anatomic models for 3D printing. Engineers can optimize the model for 3D printing by removing artifacts, adding support structures, and adding patient identification information to the model. The STL files for the final anatomic model are then exported to the printer software, where it is taken through a final printability check, and the model is printed. Afterwards, we post-process the model to prepare for delivery using a series of washing and drying cycles that can take up to a few hours. We can also add any finishing enhancements at this stage, such as clear lacquer or hand painting. The printer itself must be cleaned and reset for the next job. A delivery notification email is sent to the client, which includes a secure web-accessible digital rendering of the model, and an anatomic model record, a document containing patient and print information that serves as official record for the request. Delivery is coordinated with the clinical team, and the model is hand-delivered with instructions on how to handle and dispose of the model properly. Once the patient has surgery, we review operative notes and log pertinent feedback and review as a team.
Hi, my name is Katie Livingston, and I have been a simulation development engineer at Simpede since 2010. On our path towards developing a hospital-wide 3D anatomic modeling service, there were many challenges that had to be faced. One of our initial challenges was ensuring easy accessibility of the service to all departments within the hospital, as our customers have a high demand on their time. Therefore, a simple online request portal was created that solicits the necessary information and provides confirmation that the request has been received. This ensures their role in our process is simple and brief. The team then defined a process to manage requests through completion. This led to the assignment of roles and responsibilities, which in turn highlighted the strengths and weaknesses of the team. We chose an approach that relies on a radiologist to verify the segmented anatomic model and relies on the engineer for all else. Therefore, at the beginning of developing our service, engineers had to be mentored and permitted the time to gain expertise in understanding how different anatomical structures appear in radiological imaging. However, these same engineers have relevant technical experience using a variety of complex segmentation software, CAD software to design structural support elements, and expertise in 3D printing and additive manufacturing. Overhead and additional resource demands associated with software, hardware, and delivery of the service itself should not be underestimated, as all are crucial in providing a reliable service. Available resources are also needed for printer maintenance, debugging, repairing, and updating machines, post-processing labor demands, maintaining material supply, and developing a strategy for maintaining internal expertise. Lastly, an integral part of our process is our partnership with radiology. On a weekly basis, we meet with a radiologist to review our 3D anatomic model requests.